Good morning, friends. This video is going to be on logarithmic functions. And you'll notice that I have grabbed my notes because I am going to definitely want those until I fully understand or have a good idea of what's happening. And the very first thing we're asked to do is to convert. So I'm going to grab that small section of notes on converting and make a copy of it and bring it over to the notes. Okay, so we are given an exponent. How do I know it's an exponent? Because there is a power in the problem, 4 to the 5th power, and I'm going to change it into a logarithm. So my goal is to make it look like this when I'm finished. That is my goal for this problem. So I'm going to start with the word log. And then I'm going to notice that right here is where the variable b goes. And right here is the variable b, and that makes sense because b stands for base. So the 4 is going to go right there. Then I'm going to notice that the x goes right here, and the x is the argument or the answer to 4 to the 5th power. And so that is going to be the number 1024. And then I'm going to say that it equals, and the rule says that it is supposed to equal y, and y is the power or the exponent, which in this case turns out to be 5. So I'm going to put a 5 right there. And the thing is these are true statements. So for instance, if you grabbed the calculator and you typed in the question, I just want to show you that, first of all, the question, the equation that I gave you for the question is a true statement. So if you were to put in 4 to the 5th power, 4 to the 5th power, it does equal 1024. And if you type in your answer, which is, I'm going to hit math, I'm going to arrow up to the word log base, and my answer was that I have a 4 here, and I have a 1024 here, and when I hit enter, I get 5, and that's what I have in my work, so I know I am correct. So these are all very, very checkable on the graphing calculator without issue whatsoever. Okay, so let's do the next one. So I'm going to erase my help here. And let's look at the next one. The next one is also an exponent. So I am supposed to turn it into a logarithm. Fantastic. So I'm going to start with the word log. And I need the base number. And the base number is the base of the problem, which is the 3. So I'm going to put the 3 right here. Next, I need what is called the argument or the answer. And the argument is this number. So I'm going to put it right here. And then I'm going to put equals. And then the exponent is the next piece that I need. And the exponent is the 4. So I'm going to say that it equals 4. In other words, the logarithm says, what power of 3 gets you 81? In other words, it says, what power of 3 will get you, I think that's better, will equal 81. What power of 3 will equal, I think I like get you better, will get you 81. Or how many powers of 3, maybe that would be the better question. How many powers of 3 does it take to get to 81? How many powers of 3 does it take to get to 81? That's what a logarithm asks. Okay. The next problem, friends, gives you a logarithm. So it gives you a logarithm, so it's wanting you to convert it to an exponent. So if it wants you to convert it to an exponent, you need to start with the base. So you need to locate the base, and the base is this number right here. So you're going to write 2 as the base number. And then you need the power, and the power is that number right there. So you're going to say 6, and 2 to the 6th power is equal to 64. So all we're doing, if you will, is we're changing languages. We're changing exponentials into logarithms, or we're changing logarithms into exponentials. So it's like if you're learning a new language. If you're learning English and you speak Spanish, then you have the Spanish word, you have the English word, and you should be able to go back and forth between the English and the Spanish word. So that is what we're doing when we're converting logarithms into exponents or exponents into logarithms. We're saying the same thing using a different language, if you will. If you want to see if you're correct, again, you can grab the calculator and test it. So this is log base 2, 64 is 6. So we're going to type in log, and the way you get the log is you hit math, and you can come up here, and you're going to say log base 2, 64 is 6, and we changed it to 2 to the power of 6 is 64. See, they undo their inverses of each other. By the way, there's 2 ways to get this log. The other thing you can do is you can hit the key that says log, and you can type in 64 and close it, and then you can go divided by, and you can hit the key that says log and type in 2, and that will also get you 6. So this is what I'm saying. I'm saying that if you hit math and you arrow to log base, and you put in 2 and you put in 64, you get 6. The other way you can do that is you can just hit the log key and type in 64, and then go divided by, and hit the log key and type in 2 and hit enter, and you get the same thing. That's 2 ways of doing the exact same thing on the graphing calculator. And you're like, well, why would you ever do that? Well, because way back when, in the 1990s, 1980s, 1970s, the log key was on the calculator, but the math key was not. So back in the old day, we would have to do what's called a change of base. So that second example is a change of base. Okay. And by the way, the calculator fell asleep. All right, so let's go to the next one. Okay, the next one gave us the exponent again. So it gave us the exponent, so we're going to change it into a logarithm. So we're going to say we have a logarithm whose base is 2, whose argument is 1024, so the power had to be 10. The next one is a logarithm. We're going to turn it into an exponential. We're going to say the base of the logarithm is 5, the exponent is 7, and 5 to the 7th power is equal to 78,125. Okay? The next one, you'll notice there's not a number printed on the base. There is not a number printed on the base. If there's not a number printed on the base, then the number printed on the base should be and is the most common number used. and that is the number 10. So that's really a 10 right there. So if there's no number on the word log, its base is 10, and that is called a common log, and that's what is right over here in your notes. Okay, so that is a common log. So when you change it to an exponent, it changes to 10, 10, whose power is 4, is equal to 10,000. Now, when you have ln, notice that's not log, it's ln. That is a natural log, and the natural log has a base e. This is a natural log, and which means it has a base of e. So the base is the number e. So if I change this into a logarithm, I am going to say, or to an exponential, I'm going to say I have a base of e raised to the power of 7 is equal to 1096.63. And if you look at that on the calculator, and I do think my calculator fell asleep, so I might have to wake it back up. Oh, I'm good. The E key is on the left-hand side. So if I hit e to the power of, what was it, 7? I get 1096.63. By the way, if I would have hit natural log, 1096.63.3158, and hit enter, I would get 7. Okay, so they undo each other. That's why they're on the same key. All right. So this is an exponent. I need to write it as a logarithm. So I'm going to say I have a logarithm whose base is 10. Gives me 1, 2, 3, 4, 5, 6, 7 zeros. That's 10 million equals 7. And then, by the way, because it is a common log, a base of 10, you don't need to put the base. So you can just put that. And again, on the calculator, if you just hit that key, on the calculator, if you just hit the log key and type in 10 million, that is 1 with 1, 2, 3, 4, 5, 6, 7 zeros, and hit enter, it will tell you 7. Or if you do 10 to the power of 7, you will get 10 million. They are inverses of each other. All right, last but not least, this is a base e, which means it's going to be a natural log. So you're going to go ln of 7.39 is equal to 2. And if you want to check that, you could check your calculator and you could ask for E2 and hit enter. And if you want to check that you're right, you could go natural log 7.389056.099 and hit enter and get 2. Okay. So now that we know how to switch back and forth between between logarithms and exponents, the other thing we're going to do is there are a whole bunch of rules. If you look at these notes, there are a ton of rules for exponents, and we are going to look at specifically these properties. So we are going to look in our notes at this section right here. Okay? And you're going to use these rules so often, you're going to become very good at them. And for this day, we are going to actually look at, I think, these 4 rules right here. So let's focus right here. And let's look at what we have right here. Okay, so we have a natural log e. So when we look at this, we have a natural log e. So basically, if you don't think of it as a natural log, what we have is log e of e. Okay, that's what the pink thing means. And if you look over here in the notes, that matches up with this rule. And this rule right here said that if this base number right here and this base number right here are the same thing, it's like these are not even here and the answer is the power. So this answer is going to be, well, 3x plus 4. So that's what that equals. And I think we could probably check that on the calculator. I don't know, I've never tried that before. But let's do that. So it was a natural log e. Oh, well, we can't because it has a variable in it. Hello, come on, I'm smarter than that. But it was like, let's say it was like 3, then you hit enter and you get 3. So that's the same thing we had, only we had a variable in it. So not a big deal. All right. Then we're going to notice this next rule right here. That rule is going to be, let's see, we got a big number and then log base 7. So that looks most like this rule right here. And that says if you have a coefficient and a log base with the base number right here, this number and this number are the same number, and it says if those are not even there, and your answer is simply what that big number is. So this answer is this number right here. So that is 3x. This is 2. That's the same as question 10 and question 12 are the same type of question. One's a natural log and one's not. Not a big deal. And then the last one, you'll notice, interestingly enough, says the argument is 1. The argument is 1. That's this one right here. That's that rule. And if the argument is 1, the value is 0. So this comes out just to be the number 0. So that's what would go in the box. Because anything to the power of 0 is 1. So, I know, that's not particularly clear, but really what you want to do is match the rule. That's what you're really doing. Okay, now that we've done all that, let's look at the graphs. Sorry, I'm going to undo all this writing on my notes so that they don't show up like that in your Canvas. All right, so the reason we teach logarithms after exponents is because logarithms and exponents are inverses of each other. We've just learned how to deal with logarithms, so graphing them seems insurmountable. But we're pretty decent at graphing exponents now. So what we're going to do is we are going to do the inverse. So we are going to find the inverse of this. So we are going to find the inverse of f of x. We're going to find the inverse of this. Okay? We're going to find the inverse of that. We are going to say that x is equal to 3 plus log 2 parentheses x minus 4. And it's not x because to do inverses we switch x's and y's. So it is y minus 4. And remember, our goal is to isolate y. So our goal is to get this by itself. So the first thing we do towards that goal is move the 3. So we have x minus 3 is equal to a log whose base is 2 and whose argument is y minus 4. Our goal is to isolate y. Y is inside of a logarithm. So we are going to use the convert rule. So we are going to use this rule. And so if we use that rule, the 2 is the base, the x minus 3 is the exponent, and it equals y minus 4. If you didn't follow that, let's see if we can do this. Let me take out some color that I got going on here. All right. It was a logarithm to begin with. We have a base of b, which becomes the power, or the base number. We have a base of 2, which goes right here. Okay. Then we have, all right, then we have the argument, and the argument stays on this side of the equal sign. Excellent. Then we have, and actually I think if I'm consistent, that should have been a different color. This should be your y, and this should be your y. So, this right here goes right here. And then this piece right here is this piece right here. So this piece right here is this piece right here. Our goal is to get y by itself. So now the 4 needs to move. So we have 2 to the power of x minus 3 plus 4 equals y. I'm going to move this out of the way for the moment. All right. So now that we have that, we have we have a horizontal asymptote of y equals 4. And when we do, if we think of a table, of x values and y values, if we let the x value equal 3, so if we put a 3 in here, that would say 2 to the 0 power, which is 1. 1 plus 4 is 5. So we have the 0.35. So first of all, we have a horizontal asymptote of y equals 4. 1, 2, 3, 4. So we have a horizontal asymptote that goes right there. And that is y equals 4. We just plotted the point, or we just discovered the point 35. So 1, 2, 3 to the right, 1, 2, 3, 4, 5 to the 5 up. So there's our first point on our exponential function. Okay. Well, let's let x be 4. So if we put 4 for x, that's 4 minus 3, which is 1. 2 to the first power is 2. 2 plus 4 is 6. So now we're going to plot 4, 6. So we're going to go 4 to the right, 1, 2, 3, 4, and 6 up. 5, 6 up. There is 6 up. Awesome. So now what if x is 5? Well, if x is 5, we're going to put the number 5 right here. And 5 minus 3 is 2, and 2 to the second power is 4, and 4 plus 4 is 8. So I'm going to have the point 5, 8. 5, 6, 7, 8, which is right here. And I know the way exponentials run, the next point's not going to be on that. It's not going to be able to graph on my little piece of graph paper. So let's go the other way. Let's let x equal 2. If x equals 2, if I put a 2 here, that gives me 2 minus 3, which is negative 1, which then gives me the number 1/2, because then 2 to the negative 1 is equal to 1/2. And 1/2 plus 4 is 4 1/2. So I have the ordered pair 2, 4 1/2. So 2 to the right, 4 1/2 will be right here. And that makes sense because it's going to get closer to that asymptote. Okay, well what if I let x be 1? If I let x be 1, if I put a 1 where this x is, then I have 1 minus 3, which is 2 to the negative second. 2 to the negative second is 1 over 2 to the second, which is 1 over 4. And 1 over 4 plus 4 is 4 1/4. So 4 1/4. 1, 4 1/4 would be about right there. And then if I continued along this path, I would get closer and closer and closer and closer and closer, but I would never hit y equals 4. So my exponential function is going to look like this. Okay, that's the exponential function, but we were supposed to graph the logarithm function. So we're going to switch all the x's and y's. So we are going to switch all the x's and y's. And we're going to start with y equals 4. If we switch the x and y, that now says x equals 4. If that now says x equals 4, the vertical asymptote is x equals 4. So we're going to put in the vertical asymptote of x equals 4. 1, 2, 3, 4. The vertical asymptote of the logarithm is this line right here. That line is the line x equals 4. Why did it switch from y equals 4 to x equals 4? Because it's an inverse. And inverses switch x's and y's. All right. Now, I'm going to take this table and I'm going to switch them. And that table is going to be, what color am I doing? Let's do it in green. The table is going to be 4 1/4, 1, 4 1/2, 2, 5, 3, 6, 4, 8, 5. And I'm going to plot those points. So 4 1/4, 1. 4 1/4, 1 will be about right there. 4 1/2, 2 will be about right there. Because this is 1, 2, 3, 4, right? 5, 3 will be here. 6, 4 will be here. And remember, that was the asymptote for the other function, right? Okay, so don't let it bother you now. 8, 5. 5, 6, 7, 8. 1, 2, 3, 4, 5. Whoops, I need my green ink back. 5, 6, 7, 8. 1, 2, 3, 4, 5. So this curve is going to do, this logarithm is going to slide right up against the line, x equals 4, and then it's going to begin its curve this way. I'm going to put, and then I'm going to put in the line, y equals x. And there's the foldable. And there it is. And so the green graph is the logarithm function. The pink graph is the exponential function. And if you put it in the graphing calculator, it'll look just like that. And if you put it in Desmos, it will look just like that. Okay? Fabulous. All right. So the next one is a logarithm. And if you don't want to do what we just did on the last one, that is fine. We are going to say, because this is the number -1, we are going to have a vertical asymptote. I don't know why I'm writing in purple or in orange instead of purple. This right here says we're going to have a vertical asymptote at x equals 1. So here is x equals 1. And the entire function is going to not touch that vertical asymptote. And if you want to graph it, 3 natural log x minus 1, you can go to your graphing calculator and you can type in 3 natural log x minus 1, close it, and hit graph. And by the way, if you want, you can also put in x equals 1. Oh, you can't because it's a vertical line. It's not a function. So there we are. Okay. And then if you want to plot points, go to the table. And you'll notice everything where the x's are smaller than 1s are errors because nothing can happen until you're bigger than 1. So we can plot 2, 0. So if we plot 2, 0, we're plotted right there. If you want another point, you can plot 3 and just a little bit bigger than. Let's see if there's anything else that's actually going to be kind of nice. Let's do that one. That's 6, almost 5. So let's plot 6, almost 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So 6, almost 5 is going to be there. Did you notice 7 was a little bit bigger than 5? 7 is a little bit bigger than 5. So 7, a little bit bigger than 5, would be about right there. And if you want to put all those other points in, you can. If you want to put in points bigger than 1 but smaller than 2, you can come here to table set. And you can say start at 1 and go by tenths. Okay? So 1 is an error, but notice 1.1 is negative 6.9. So 1.1 is negative 6.9. So 1, 2, 3, 4, 5. Negative 6.9. So that's like right there. Okay, and then if you look at 1.2, that's almost negative 5. So 1.2 is almost negative 5. So 1.2 is almost negative 5. So 1, 2, 3, 4, so about right there. And then it keeps doing this. It does this. There you go. And that would be that. So, super cool. All right, my friends. That is the beginning, the introduction to logarithms. If you have any questions, email me or ask me in class. Have a great day.